Assalamualaikum. My name is Bushra Rizvi, roll number 7, and my topic for today's presentation is scandium aluminum nitride alloy. This alloy is shaping the future of electronic, sensing, and even artificial intelligence. So, in this topic, we will discuss the introduction, historical development, composition, synthesis, application, comparison of scandium aluminum nitride with other piezoelectric material, sustainability, challenges, and future prospect. So, first of all, we will discuss the introduction. Scandium aluminum nitride is an advanced functional alloy which belongs to the group of 3 nitride material, which also include aluminum nitride, gallium nitride, and indium nitride. Now, aluminum nitride itself is a very useful material because of its thermal stability, CMOS compatibility, and piezoelectricity. But it has one big drawback: its piezoelectric response is relatively weak. That's why scandium comes in. By adding even a small amount of scandium to the aluminum nitride lattice, we can dramatically enhance its piezoelectric properties without sacrificing its thermal stability and environmental safety. But scandium aluminum nitride does not just stop at being a better piezoelectric. At higher scandium concentration, it does something remarkable. It becomes ferroelectric. That means its electric polarization can be switched on and off. This opened door to the neuromorphic computing, non-volatile memory, and tunable RF devices. So in short, this alloy is a multifunctional alloy for the next generation technology. Now, historical development of scandium aluminum nitride alloy. The development of scandium aluminum nitride alloy is closely linked to the broader research progress in 3 nitride materials. Aluminum nitride itself was first explored in the mid-20th century for its insulating and thermal properties. However, its piezoelectric potential began to gain attention in the late 20th century with the rapid growth of RF, radio frequency communication technologies, and thin film deposition techniques. The breakthrough in scandium aluminum nitride research occurred in the early 2000s when first principal density functional theory (DFT) calculation predicted that alloying aluminum nitride with transition metals such as scandium could significantly enhance its piezoelectric properties. These predictions were experimentally validated in 2009 when Ikeyama and co-workers demonstrated an unprecedented increase in piezoelectric coefficient of scandium aluminum nitride thin films deposited by reactive magnetron sputtering. This landmark study showed that introducing approximately 30 to 40% scandium into the aluminum nitride lattice results in a dramatic enhancement of piezoelectric response. Following this discovery, intensive research efforts focused on understanding the origin of this enhancement. Subsequent studies revealed that the key mechanism lies in the proximity of vertice scandium aluminum nitride structure to a competing hexagonal or rock salt phase of the scandium nitride. This structural instability leads to elastic softening along the polar axis, enabling large polarization changes under applied mechanical stress. Between 2010 and 2015, significant progress was made in optimizing thin film growth condition, controlling crystallography orientation, and minimizing phase separation at high scandium concentration. From 2015 onwards, scandium aluminum nitride rapidly transitioned from a laboratory curiosity to an industrially relevant material, particularly in the field of RF bulk acoustic wave filters for 4G and 5G communication systems. More recently, research has shifted toward exploring ferroelectricity in scandium aluminum nitride, domain switching behavior, and artificial intelligence-assisted material optimization. This is the diagram that represents the history of scandium aluminum nitride alloy. Now we will discuss the composition of scandium aluminum nitride alloy, which is very important because in material sciences, the atomic scale properties directly influence the macroscopic properties of material. So this is the ternary nitride alloy because it is formed by the combination of 3 elements, scandium, aluminum, and nitride. That is why the term ternary used here. It is formed by substituting scandium into the aluminum nitride lattice. Its general formula is expressed as scandium X, where X is the concentration of scandium or molar fraction of scandium. Aluminium 1 minus X is the concentration of aluminum, and N for the nitride. For example, if we have X is equals to 0.1, which is the concentration of scandium, then the composition of aluminum becomes 0.9. In practical thin film application, because this alloy fabricated in the form of thin film, scandium content is typically limited up to 0.43 in order to preserve the wazite structure, crystal structure, and functional properties. Now, question arises why we choose scandium as alloy in order to incorporate into the aluminum nitride alloy. The reason is because of its larger ionic radius and distinct electronic configuration as compared to the aluminum. Scandium ions induce significant local lattice distortion and internal strain when incorporated into the aluminum nitride matrix, allowing precise tuning of elastic, dielectric, and piezoelectric properties. This compositional flexibility makes this alloy a highly engineerable functional material for MEMS, RF, and electromechanical application. In the scandium aluminum nitride lattice, scandium atoms substitute or replace the aluminum atoms at the cation sites rather than occupying interstitial position. Both scandium and aluminum cations maintain the positive 3 oxidation state, ensuring the electrical charge neutrality because the charge on the nitride is -3, while nitrogen occupies the anion sublattice throughout the composition range. The alloy forms a continuous solid solution under metastable Wurtzite conditions without forming discrete compounds at intermediate composition. Next is crystal structure of scandium aluminum nitride. At low to the moderate scandium concentration, this alloy retains the hexagonal Wurtzite crystal structure, which is inherited from the pure aluminum nitride. This structure belongs to the non-centrosymmetric space group P63MC, which is the key requirement for piezoelectric behavior. In the Wurtzite structure, each metal cation, aluminum or scandium, is tetrahedrally coordinated with 4 nitrogen atoms. The unit cell is defined by the lattice parameters A and C, along with an internal positional parameter, which is U, that describes the relative displacement of nitrogen atom along the C-axis. The absence of inversion symmetry along the axis gives rise to spontaneous polarization in the crystal. When scandium atoms replace the aluminum atoms in the lattice, they occupy the same cation sites without changing the basic hexagonal symmetry at the low scandium content. However, because the ionic radius of scandium is larger than that of aluminum, the substitution leads to lattice expansion and local structural distortion. These distortions primarily affect the metal-nitrogen bond length and angles, resulting in a less rigid tetrahedral coordination environment. As you can see, this is the lattice structure, Wurtzite crystal structure of aluminum nitride, and in this, each cation is surrounded by the 4 anion, which is nitrogen. Similarly, each nitrogen is surrounded by the 4 aluminum ion. As the scandium concentration increases in the alloy, systematic changes occur in the crystal geometry. One of the most significant effects is the reduction in the Ca ratio, which is the lattice parameter C and A, which indicates a gradual flattening of the Wurtzite unit cell along the polar C-axis. In this diagram, you can see this is the lattice parameter A and this is the lattice parameter C. When scandium concentration increases, then this ratio, C ratio A, reduces. As scandium is introduced into the lattice, both lattice parameters A and C increase due to large atomic radius of scandium as compared to the aluminum. The ionic radius of aluminum is 53.5 picometer and that of scandium is 74.5 picometer, which is approximately 40 times larger than that of aluminum. The increase in the A parameter is more pronounced than the C, resulting in reduced Ca ratio. This deviation from the ideal Wurtzite geometry generates internal strain and facilitates polarization rotation under applied stress. At the same time, the internal parameter U deviates from its ideal Wurtzite value, reflecting a shift in the nitrogen atom position. These structural changes led to elastic softening of the lattice, making the crystal become more compliant under mechanical stress. This softening is closely linked to the enhanced piezoelectric response observed in scandium aluminum nitride alloy. Importantly, despite this distortion, the long-range Wurtzite symmetry is preserved up to the critical scandium concentration, making the material structurally stable enough for device application. Now, phase stability and structural transition. The phase stability of scandium aluminum nitride is governed by the competition between two different crystal structures. The first one is Wurtzite phase, which is preferred by aluminum nitride, and the rock salt cubic phase, which is stable structure of scandium nitride. This structural competition plays a very important role in determining the compositional limits of the alloy. As we know, at the low scandium concentration, the Wurtzite phase remains energetically favorable. However, as the concentration of scandium increases, the Finney energy difference between the Wurtzite and rock salt phases decreases. This makes the Wurtzite structure progressively less stable and more susceptible to the transformation. The phase stability of scandium aluminum nitride is governed by the balance between the thermodynamic driving force and kinetic constraints during the film growth. For the scandium concentrations up to approximately x is equals to 0.40 to 0.43, the word-side phase of scandium aluminum nitride can be stabilized, particularly in thin film form. In this composition range, the word-side structure is desirable metastable, meaning it is not the lowest energy phase under equilibrium condition, but can exist due to kinetic constraints. Here is a diagram which shows the phase stability of scandium aluminum nitride. The stabilization of metastable word-side scandium aluminum nitride is typically achieved through non-equilibrium deposition techniques such as reactive magnetron sputtering, factors such as rapid film growth, substrate-induced strain, and limited atomic diffusion suppress the formation of the energetically favored rock salt phase. Beyond the critical scandium concentration, the alloy tends to undergo phase separation or transform into the cubic rock salt structure, which leads to the degradation of the piezoelectric and structural properties. Here is a table which shows a different scandium concentration, different functional effect. For example, if we have scandium concentration 0, x equals to 0, then dominant crystal phase is word-side hexagonal. This is thermodynamically stable. And in this high Ca lattice parameter ratio, stiff lattice, strong covalent aluminum nitrogen bond, and its piezoelectricity is moderate. But when the concentration increases up to 0.2, then again the crystal structure is word-side, thermodynamically stable, but slight lattice expansion, minor bond softening, gradual enhancement in the piezoelectric coefficients. But when the scandium concentration increases up to 0.3, then the structure is metastable word-side structure, and there's a strong increase in piezoelectric response. And when the concentration increases up to 0.43, then the word-side structure is highly metastable and maximum piezoelectric and ferroelectric performance. When concentration is 0.43 to 0.50, then acoustic loss increases, degradation begins. And concentration above the 0.5, then the alloy exists in rock salt structure, which is thermodynamically stable, but loss of piezoelectric and ferroelectric properties occur. Temperature is another critical factor. Elevated deposition or annealing temperature can relax the lattice towards the thermodynamically favored rock salt structure, particularly at high scandium content. Careful control of growth parameters is therefore essential to maintain the metastable word-side phase and exploit scandium aluminum nitride exceptional piezoelectric properties. Here's a diagram which represents the word-side structure and the rock salt structure. Next is bonding nature and electronic structure of scandium aluminum nitride, which is again very important because the bonding, the crystal structure, the lattice structure all greatly influence the macroscopic properties of the material. The bonding in scandium aluminum nitride is a combination of ionic and covalent interactions between the cations and anions, which is nitrogen. In aluminum nitride, aluminum nitrogen bonds are strong, directional, and partially ionic, reducing a rigid tetrahedral lattice. As scandium substitute into the lattice, it's modify this framework. The large ionic radius and more diffuse 3D orbitals of scandium create longer, weaker, and more ionic scandium-nitrogen bonds. Density functional theory study shows that scandium incorporation reduces bond directionality, bond force constant, particularly along the C-axis. This bond softening increase lattice compliance, allowing larger atomic displacement under mechanical stress and enhancing piezoelectric response. Electronically, scandium introduces hybridized 3D 2p states closer to the conduction band, slightly reducing the band gap while maintaining a wide band gap semiconductor behavior. The proximity to the structural instability between word-side and rock salt phase creates a soft mode where small mechanical strains induce large polarization changes. This mechanism explains the dramatic increase in piezoelectric coefficients, which is represented by D33, and electromechanical coupling in scandium aluminum nitride. Here's a diagram which shows when the scandium atom introduces into the aluminum nitride lattice, then the result is bond softening and increased ionic polarization, which affect the macroscopic property and increases piezoelectric coefficient up to 4 to 5 times, and electromechanical coupling increases 3 to 4 times, which affect device level impact. For example, wider bandwidth, increase the sensitivity of sensors, and energy harvesters, more power. Now, The next point is synthesis and fabrication methods of scandium aluminum nitride. So scandium aluminum nitride is primarily synthesized in the form of thin films. Typically, scandium aluminum nitride film thickness ranges from 100 nanometer to several micrometer, depending on the application. Thin films are required for high-frequency devices, while thicker films are used in MEMS actuators. Uniform thickness is essential to ensure the consistent device performance. Bulk synthesis is extremely difficult due to its high melting point and phase instability at high scandium concentration. Therefore, physical vapor deposition techniques are predominantly used for its fabrication. Among these, reactive magnetron sputtering is the most widely and commonly used method. So let's talk about reactive magnetron sputtering. So it is a vacuum-based physical vapor deposition technique widely used for the fabrication of compound thin films. In this process, atoms are ejected from a solid target through bombardment by high-energy ions and subsequently react with a reactive gas to form a compound film on a heated substrate. Due to its excellent controllability, scalability, and compatibility with the semiconductor manufacturing, reactive magnetron sputtering is the most commonly employed method for synthesizing high-quality scandium aluminum nitride thin films. For scandium aluminum nitride deposition, either a pre-alloyed aluminum scandium metallic target or separate aluminum and scandium targets may be used. Nitrogen serves as the reactive gas responsible for nitride formation, while argon is used as the sputtering gas to sustain the plasma and enable efficient momentum transfer to the target surface. The deposition process is carried out in a high vacuum PVD chamber. Prior to film growth, the chamber is evacuated at an ultra-low base pressure to remove residual oxygen, moisture, and other contaminants that could degrade film purity and adhesion. Once the desired vacuum level is achieved, argon gas is introduced and the plasma is ignited using an applied electric field. High-energy argon ions generated within the plasma bombard the aluminum-scandium target, causing aluminum and scandium atom to be physically ejected via the momentum transfer. Simultaneously, nitrogen gas is introduced into the chamber where it reacts with a sputtered metal atom, either in the gas phase or on the substrate surface. This reactive process leads to the formation of scandium aluminum nitride thin films on the substrate. For industrial scale manufacturing, pre-alloyed scandium aluminum scandium targets are preferred because they ensure uniform scandium distribution throughout the film and offer high process reproducibility. In contrast, co-sputtering from separate aluminum and scandium targets is primarily used in the research and development environments where precise tuning of scandium concentration is required. Typically, the scandium content is maintained within the range of 20 to 35 atomic percent, as high concentration significantly increase the risk of phase instability. The sputtering atmosphere consists of a carefully controlled mixture of argon and nitrogen gases. Argon plays a very critical role in sustaining the stable plasma and enabling efficient sputtering of the metallic target. Nitrogen acts as a reactive species, forming strong metal-nitrogen bonds essential for scandium aluminum nitride film growth. Precise control of nitrogen partial pressure is critical. Insufficient nitrogen supply results in metal-rich films with poor electrical and piezoelectric properties, whereas excessive nitrogen can lead to target poisoning, reduced sputtering rates, and process instability. Optimizing the nitrogen to argon ratio is therefore essential for achieving stoichiometric high-quality scandium aluminum nitride films. This is the diagram. Several deposition parameters strongly influence the structural and functional properties of scandium aluminum nitride thin films. These include substrate temperature, sputtering power density, nitrogen to argon gas ratio, and scandium concentration in the target. Substrate temperature typically range from 300 to 600, with elevated temperature promoting enhanced surface diffusion and improved crystallinity. Silicon substrates are most commonly used due to their compatibility with CMOS and MES technologies. Sapphire and silicon carbide substrate are also employed. Prior to deposition, substrates undergo thorough cleaning to ensure strong film adhesion and defect-free growth. During the film growth, aluminum and scandium atoms react with nitrogen and arrange into the hexagonal versite crystal structure. The incorporation of scandium into the aluminum nitride lattice distort the lattice and metal-nitrogen bond softening, which are directly responsible for enhanced piezoelectric properties of scandium aluminum nitride alloy. Post-depositional thermal annealing is often applied to further improve crystal quality, reduce residual stress, and enhance electromechanical performance. Effective stress management is particularly important for ensuring long-term reliability in RF and MEMS devices. Now, advantages and limitations. Although it is a very good technique to form scandium aluminum nitride thin film, but it has certain limitations and advantages. First of all, let's talk about the advantages. It offers excellent control over thin film composition, uniform deposition over large areas, and full compatibility with existing semiconductor fabrication processes. Make it well suited for industrial scale production of scandium aluminum nitride thin films. However, high cost of scandium targets, the risk of phase separation at elevated scandium concentration, and the presence of residual stress in the thin films remain key challenges that require careful process optimization. The next technique is co-sputtering technique. In this, separate aluminum and scandium targets are used instead of the pre-alloy target. The relative power applied to each target controls the scandium concentration in the film, and it enables very precise tuning of scandium content and ideal for research and optimization studies. The next is molecular beam epitaxy. It is an ultra-high vacuum thin film deposition technique in which highly controlled atomic or molecular beams of constituent elements are directed into the heated substrate, enabling layer-by-layer epitaxial growth with atomic precision. Scandium aluminum nitride thin films are grown under ultra-high vacuum conditions, typically at the base pressures below 10 into 10 minus 10 torr, which minimizes contamination and enables precise control over film composition and structure. High purity aluminum and scandium are supplied from solid source diffusion cells, where the source material are heated to carefully regulated temperatures to generate stable atomic fluxes. Nitrogen is introduced in an activated form, usually via the radio frequency or electron cyclotron resonance ECR plasma source, which dissociate molecular nitrogen into the highly reactive nitrogen radical. These reactive species, as we know that the free radicals, highly reactive species, are essential for efficient nitride formation at the moderate growth temperatures. The atomic beams are directed toward the single crystal substrate, such as gallium nitride or aluminum nitride templates on silicon, which is maintained at the temperature ranges between 500 degrees Celsius and 800 degrees Celsius. Upon reaching the substrate surface, the atoms migrate, nucleate, and incorporate into the growing lattice. The scandium concentration is precisely controlled by adjusting the flux ratio of scandium to aluminum, which is continuously monitored using in situ diagnostic tools such as reflection high energy electron diffraction. Due to the extremely slow growth rates, often below 1 micron meter per hour, this technique controls monolayer level thickness, automatically abrupt interfaces, and fabrication of superlattices and compositionally graded structure. The resulting film exhibits exceptionally low defect densities, making this technique valuable for fundamental studies of structure property relationships in scandium aluminum nitride. Here is a diagram of this technique. Now next move toward metal organic chemical vapor deposition, MOCVD. It is a vapor phase epitaxial growth technique in which volatile metal organic precursors undergo chemical reactions on a heated substrate to form thin films. In this technique, gaseous precursors are transported into the heated reaction chamber under controlled flow conditions. Commonly used precursors include trimethyl aluminum for aluminum, tris cyclopentadienyl scandium for scandium, and ammonia as the nitrogen source. Substrates such as sapphire or silicon carbide are typically heated to 800 degrees Celsius to 1100 degrees Celsius, enabling thermal decomposition of the metal organic compound. Upon reaching the hot substrate surface, the precursor decomposes, releasing aluminum and scandium atoms that react with cracked ammonia to form the alloy. The alloy composition is governed by the molar flow rates of TMA and tris cyclopentadienyl scandium, while growth proceeds under reduced pressure in a laminar flow regime, ensuring good thickness uniformity across the large wafers. A major challenge in this alloy is the poor thermal stability and low vapor pressure of tris cyclopentadienyl scandium, which restricts achievable scandium incorporation. Additionally, incomplete decomposition of the organic ligands can introduce carbon contamination, adversely affecting film impurity and electrical properties. The next is chemical vapor deposition. This is another approach to fabricate scandium aluminum nitride into the thin films. In this, halide precursors such as aluminum trichloride and scandium trichloride are vaporized and transported by the carrier gas into the hot wall reactor. Ammonia is introduced separately as a nitride source, and the precursors react at elevated temperature, typically around 1000 degrees Celsius, to deposit scandium aluminum nitride on the substrate. However, high thermostability and similar decomposition temperature of the aluminum and scandium chlorides make independent control of their incorporation difficult. This often results in poor compositional precision and limits the applicability of conventional CVD for scandium aluminum nitride growth. Next one is property of this alloy, which is very important. First one is piezoelectric property. Piezoelectricity is the ability of the material to generate electric polarization in response to the applied mechanical stress and conversely to undergo mechanical deformation when subjected to an external electric field. This phenomenon exists exclusively in materials with non-stereosymmetric crystal structure, as we know that scandium aluminum nitride lacks a center of symmetry, making it excellent piezoelectric material. The incompression of scandium into the aluminum nitride dramatically enhances its piezoelectric response by the bond softening. This enhancement arises from lattice softening, increased internal atomic displacement, modified bond characteristics, all of which contribute to the stronger electromechanical coupling. So first one is piezoelectric strain coefficient, which is D33. Piezoelectric strain coefficient quantifies the induced mechanical strain along the polar axis per unit applied electric field. It is one of the most critical parameters for evaluating piezoelectric performance in thin film devices. Pure aluminum nitride exhibits a relatively low piezoelectric strain coefficient, which is 5 to 6. In contrast, scandium aluminum nitride shows a remarkable enhancement with increasing scandium concentration, and the value ranges between 12 and 80 picometer volt per minute. This represents an enhancement of approximately 4 to 5 times compared to the aluminum nitride. The significant increase in piezoelectric strain coefficient enables more efficient conversion between the electrical and mechanical energy, which is essential for high performance MEMS actuators, bulk acoustic wave resonators, and RF, which is radio frequency filter technology used in 4G and 5G communication. Piezoelectric stress coefficient describes the electric polarization generated per unit applied mechanical stress. In scandium aluminum nitride, it increases sustainably with scandium incorporation due to the enhanced ionic displacement and reduced bond stiffness along the C-axis. Electromechanical coupling measures the efficiency of energy conversion between the electrical and the mechanical domains. Scandium aluminum nitride exhibits a 3 to 4-fold increase in electromechanical coupling coefficient as compared to the pure aluminum nitride, making it one of the most efficient piezoelectric thin film material available. The second property, which is shown by scandium aluminum nitride, is ferroelectricity. Ferroelectricity is the property of a material to exhibit a spontaneous electrical polarization that can be reversibly switched by the application of an external electric field. Conventional ferroelectric materials such as barium titanate and lead zirconate titanate typically derive this behavior from temperature-driven natural phase transition. Scandium aluminum nitride represents a newly discovered class of ferroelectric materials in which switchable polarization arises when within a Wurtzite crystal structure without undergoing the classical phase transition. The emergence of ferroelectricity in scandium aluminum nitride is strongly dependent on scandium concentration. At low scandium content, the material exhibits enhanced piezoelectric behavior but remains non-ferroelectric. As the scandium concentration increases, the energy barrier for polarization switching decreases. Typically, stable ferroelectric behavior is observed when the scandium concentration exceeds approximately 27 to 30 atomic percent. Below this threshold, this alloy remains in the transitional regime characterized by polarization instability but incomplete switching. As the concentration increases, the corrosive field is reduced. However, excessive scandium incorporation increases the risk of phase instability, particularly transformation towards the nonpolar rock salt scandium nitride phase. Ferroelectric scandium aluminum nitride thin film display well-defined polarization electric field hysteresis loops confirming the presence of reversible polarization. Reported Remnant polarization values typically range from 70 to 100 micron coulomb centimeter minus 2, which are significantly higher than those of many conventional ferroelectrics. The high breakdown strength and wide band gap of scandium aluminum nitride enable reliable ferroelectric operation at high electric field without premature dielectric failure. Third property is structural and mechanical properties. As we know that crystal structure maintains the oversight hexagonal structure of aluminum nitride up to the critical scandium concentration 40 to 50%. Beyond this, it is converted into the rock salt phase structure. Lattice constant. Scandium substitution linearly increases lattice parameter A and C. As a result, causes reduction in CA ratio. Stiffness. Elastic constant generally decrease with increasing scandium content. The material becomes softer. Stress. Scandium aluminum nitride thin films can be deposited with controlled stress from tensile to compressive, which is critical for MES device design and reliability. Now we will discuss the electrical properties, which are also very important. Band gap. The band gap decreases linearly as the concentration increases. This can be tuned for optoelectronic applications in the deep UV range. Dielectric constant. The relative permittivity increases with the scandium content, which is a trade-off to consider in device design for capacitor-based sensors. Thermal sensitivity. Scandium aluminum nitride films are generally stable up to temperature greater than 800 degrees Celsius, and their thermal conductivity expected to be lower than the aluminum nitride, which is itself a good thermal conductor. So this is the table that represents various properties of scandium aluminum nitride. When the scandium introduces into the aluminum nitride, then piezoelectricity increases, electromechanical coupling increasing, ferroelectricity increases, but at the specific concentration, band gap decreases, acoustic velocity moderate decreases, stiffness decreases, dielectric constant increases, and phase stability decreases, which is a challenge for high scandium deposition. Now let's move toward the application. For piezoelectric applications, scandium concentrations are typically maintained between 10 to 30%, where scandium aluminum nitride remains structurally stable in the wordite phase while exhibiting significantly enhanced piezoelectric coefficients. The film is sandwiched between metal electrodes such as molybdenum, titanium, aluminum, or platinum to form captivative or resonant structure. The stacks are then patterned using standard lithography and etching techniques to fabricate resonators, sensors, and actuators. For ferroelectric applications, higher scandium concentration, approximately 27 to 40%, are employed. Scandium nitride aluminum film is engineered to support reversible polarization switching along the C-axis. Ferroelectric capacitors are formed by depositing scandium aluminum nitride between the top and bottom electrodes, followed by electrical conditioning to stabilize the polarization state. Stress engineering, film thickness optimization, substrate selection are critical design parameters. Compressive stress and epitaxial alignment are often used to stabilize ferroelectricity and enhance electromechanical performance. First application, they are used in RF filters for the wireless communication, 5G and 6G and beyond. The most mature and commercially significant use of scandium aluminum nitride is in the RF, which is radio frequency acoustic filters for the modern wireless communication system. These alloy are incorporated into bulk acoustic wave and surface acoustic wave resonators, which act as frequency selective elements in smartphones, base station, and satellite communication hardware. In these devices, scandium aluminum nitride serve as an active piezoelectric layer, converting electrical signal into acoustic waves and back. The enhanced electromechanical coupling coefficient of scandium aluminum nitride enables wider bandwidth filters with lower insertion loss compared to the conventional aluminum nitride-based filters. This is essential for 5G and emerging 6G technologies, which require high data rates and dense frequency allocation. Next is MEMS sensors and actuators. Scandium aluminum nitride is extensively used in micro-electromechanical system, which is abbreviated as MEMS, where it functions as the electromechanical transduction layer. In these devices, applied electrical signal induced mechanical motion or mechanical stimuli generate measurable electrical outputs. In ultrasonic sensing, scandium aluminum nitride-based piezoelectric micro-machined ultrasonic transducers are fabricated by battering suspended membranes coated with scandium aluminum nitride thin films. These devices are used in proximity sensing, gesture recognition, ultrasonic fingerprint readers, and medical imaging system. The enhanced piezoelectric response of scandium aluminum nitride improves acoustic output pressure and detection sensitivity, enabling compact, low-power operation. The next is ferroelectric memory and neuromorphic computing. At higher scandium concentration, scandium aluminum nitride, as we discussed above, it exhibits ferroelectric behavior, enabling its use in non-volatile memory and emerging computing technologies. In ferroelectric random access memory, scandium aluminum nitride thin films are used as the active layer in the metal ferroelectric metal capacitor structure. Information is stored in the direction of polarization, which remains stable even when the power is removed. Compared to the traditional ferroelectric materials, these alloy offer superior thermostability, high remnant polarization, and excellent compatibility with CMOS fabrication processes. These attributes make it a strong candidate for embedded memory application in harsh environment. Next is tunable and reconfigurable RF components. The coexistence of piezoelectricity and ferroelectricity in scandium aluminum nitride enables electrically tunable RF components by switching or modulating the ferroelectric polarization. The resonant frequency and impedance of scandium aluminum nitride-based devices can be dynamically adjusted after the fabrication. This capability is exploited in tunable filters, phase shifter, adaptive machining network used in software-defined ratios, configurable antennas, and conjugative radar system. The scandium aluminum nitride is also used in radio frequency MEMS switches and tunable capacitors, where low loss, high isolation, and long-term reliability are critical. The next is this alloy is also used in high power and high temperature electronics because it has a wide band gap and it is used in power electronic devices. In particular, scandium aluminum nitride can be integrated as polarization enhanced barrier layer in high electron mobility transistors. The strong polarization fields in scandium aluminum nitride induce a high density two-dimensional electron gas, improving current density and power efficiency. These devices are suitable for high voltage, high frequency, high temperature operation, making this alloy attractive for power converters, RF amplifiers, electronics designed for extreme environments such as space and nuclear systems. Photonics and advanced acoustic devices. Scandium aluminum nitride tunable bandgap enable its use in deep ultraviolet optoelectronics, including UV LEDs and laser diodes for sterilization, sensing, and water purification. Its strong piezoelectric and non-linear optical properties also support acousto-optic modulation and integrated photonic devices. This is a chart that represents different applications of this alloy. Now next is the comparison of scandium aluminum nitride with other piezoelectric material. For example, aluminum nitride, lead zirconate titanate, which is PZT, and emerging hafnium oxide. Pure aluminum nitride has been the industry standard for RF acoustic devices for several decades due to its excellent thermostability, wide bandgap, low dielectric loss, and seamless compatibility. However, its relatively low piezoelectric coefficients and modest electromechanical coupling factors limit device bandwidth and efficiency, particularly for advanced wireless communication standards. Scandium aluminum nitride addresses these limitations through the incorporation of scandium, which induces lattice softening and enhancing internal polarization. As a result, scandium aluminum nitride exhibits several-fold improvements in piezoelectric response while retaining the key advantages of aluminum nitride. Now here is a comparison of scandium aluminum nitride with the conventional PZT, which is lead zirconate titanate alloy. PZT possesses exceptionally high piezoelectric coefficients and has historically dominated actuator and sensor technology. Despite its outstanding electromechanical response, PZT suffers from the significant drawbacks that limit its applicability in modern integrated systems. These include lead toxicity, incompatibility with silicon processing, and high dielectric losses at the radio frequencies and degradation under temperature, high temperature or harsh environmental conditions. While scandium aluminum nitride does not achieve the extreme piezoelectric constraints of PZT, it offers superior performance at high frequencies, great thermal robustness, environmental safety, and direct integration with the semiconductor technologies. So scandium aluminum nitride is strongly favored in radio frequency devices. Hafnium oxide-based ferroelectric represent a newer class of materials that have attracted attention due to their compatibility with advanced CMOS nodes and their ability to exhibit ferroelectric switching at nanometer scale thickness. However, this alloy-based systems typically display limited piezoelectric response, relatively high leakage current, and reliability challenges such as wake-up effects and degradation. In comparison, scandium aluminum nitrides provide a strong combination of strong piezoelectric coupling, low leakage, high breakdown strength, and excellent fatigue resistance. So overall, scandium aluminum nitride bridges the performance gap between traditional ceramic ferroelectrics and modern semiconductor compatible materials. The next point is sustainability and alignment with Sustainable Development Goals, SDGs. Scandium aluminum nitride also contribute meaningfully to energy efficiency, particularly in wireless communication technologies. RF filters and resonator based on scandium aluminum nitride exhibit lower insertion losses, high bandwidth efficiency compared to conventional material, leading to reduced power consumption in mobile devices, base stations, and communication infrastructure. These improvements directly support Sustainable Development Goal 7, affordable and clean energy, by enabling more energy efficient electronics and lowering the energy demand associated with high speed data transmission. The exceptional thermostability, mechanical robustness, and resistance to electrical fatigue of scandium aluminum nitride enhance device longevity. This support SDG 12 responsible consumption and production by promoting durable materials, efficient resource utilization, and sustainable manufacturing practices. From an innovation and infrastructure perspective, scandium aluminum nitride plays a critical role in enabling advanced technologies such as 5G, 6G communication system, IoT, sensors, energy harvesting devices, and smart MES platforms. These technologies are central to SDG 9, which is Industry Innovation and Infrastructure, as they support digital connectivity, intelligent monitoring, and efficient industrial system. Although scandium aluminum nitride is a very useful alloy because of its high piezoelectricity and ferroelectricity, but it has certain challenges. One of the most significant challenges associated with this alloy is the high cost of scandium. Scandium is a rare element with limited global supply, and its extraction and purification are expensive. As a result, high scandium content targets and thin film sustainability increase manufacturing costs, particularly for large area wafer processing and high volume production. This economic constraint motivates ongoing research into the scandium efficient compositions and alternative alloying strategy. Another critical challenge is the structural instability of scandium aluminum nitride at high scandium concentration. While moderate scandium incorporation enhances piezoelectric and ferroelectric properties, excessive scandium content, typically above 40 atomic percent, destabilizes the structure. This instability promotes phase separation, leading to degradation of electromechanical performance and reduced device reliability. The deposition of high-quality scandium aluminum nitride thin films represents additional complexity. Techniques such as reactive magnetron sputtering and molecular beam epitaxy require precise control of process parameters, including substrate temperature, nitrogen partial pressure, sputtering power, and scandium distribution. Small deviations can result in compositional non-uniformity, poor crystallographic orientation, or defect formation. Although scandium aluminum nitride demonstrate excellent performance in laboratory scale devices, long-term reliability data under real operating conditions remain limited. Compared to established piezoelectric materials such as aluminum nitride and PCT, there is relatively little information on aging behavior, fatigue mechanism, failure modes in large-scale manufacturing environments. This lack of extensive lifetime data currently limits confidence in scandium aluminum nitride for some mission-critical applications. Now, what is the future of this alloy? Despite these challenges, scandium aluminum nitride has a highly promising future, driven by strong industrial demand and rapid advances in material engineering. One of the most important growth drivers is the continued expansion of 5G and the development of 6G wireless communication technology. The need for wider bandwidth, higher frequency operation, and improved signal integrity ensures that scandium aluminum nitride based RF filters and resonators will play a central role in next generation RF front end modules. In the fields of MEMS and nano electromechanical systems, scandium aluminum nitride is expected to enable smaller, more sensitive, and more energy efficient devices. Its strong piezoelectric response, mechanical robustness, and compatibility with silicon processing, making it ideal for advanced sensors, actuators, ultrasonic transducers, and vibration energy harvester, particularly in compact and low power systems. From an environmental perspective, scandium aluminum nitride lead-free composition position is as a sustainable alternative to conventional lead-based piezoelectrics. Looking further ahead, the integration of scandium aluminum nitride with photonic and quantum technologies represent an exciting frontier. Its optical transparency, strong piezoelectric coupling, and ferroelectric tunability open new possibility for optic modulators, integrated photonic circuits, frequency converters, and quantum sensors. As device requirements become more demanding, the integration of artificial intelligence and machine learning is emerging as a powerful tool to accelerate the design, synthesis, and optimization of scandium aluminum nitride-based materials. AI algorithms, particularly deep learning and predictive modeling, can analyze large datasets from experimental and computational studies to predict optimal scandium conservation for maximizing piezoelectric coefficient, lattice stability limits, and phase transformation thresholds, effects of substrate strain, and deposition parameters on thin film quality. By combining first principle calculation (DFT) theory with AI, researchers can screen thousands of hypothetical compositions in silico before experimental synthesis, significantly reducing time and cost. In thin film deposition techniques such as reactive magnetron sputtering, AI can monitor and control parameters in real time, including deposition rate, gas composition, argon and nitrogen ratio, substrate temperature, and bias. This allows for precise stabilization of the metastable word-side phase at high scandium concentration, which is critical for achieving superior piezoelectric performance. Additionally, AI-powered imaging and spectroscopic analysis can rapidly characterize crystal structure, strain, and defects, providing instant feedback to optimize film quality. Now, conclusion, scandium aluminum nitride has established itself a transformative material at the intersection of material science and artificial intelligence. Its enhanced piezoelectric and emergent ferroelectric properties enable high-performance sensors, ultrasonic transducers, energy harvester, and neuromorphic computing devices, providing precise, low-power, and multifunctional capabilities. Furthermore, AI-assisted optimization of scandium aluminum nitride deposition and composition enhances device performance and scalability. Its continued development promises to drive innovations in intelligent systems, sustainable electronics, and high-frequency applications, bridging the gap between advanced functional material and emerging AI technologies. Thank you.